All right, so we have looked at the rational root theorem, we've looked at the integer root theorem, and we've been solving polynomials. In this short video, we're going to look at two examples of how else we can solve polynomials of higher degree. So we're going to solve this cubic polynomial right here. We're going to solve it by grouping, and this is a method that sometimes works, sometimes doesn't. You got to be kind of careful when you're looking for it, and it is kind of tough to deal with unless you quickly recognize that you can do it. But anyway, here we go. So what I'm going to do is I'm going to split apart this minus 5x. I'm going to rewrite this as x cubed plus 2x squared plus x minus 5x minus 6. Minus 6x minus 6. So you might ask, why would I want to do that? Well, bear with me here. Now I'm going to group this into two groups. And if you look at the first three terms, we can take an x out of all of them. We get x squared plus 2x plus 1. And we can factor a negative 6 out here. And you might be thinking, well, I've done factoring by grouping before, and you know, those two terms that you have there, they don't have any common factor. Well, they do actually. I just have to go a step further. This is a perfect square trinomial. Now these two things have a common factor of x plus 1 that I can take out. So there's that common factor of x plus 1. Now we write down the leftovers. X times x plus 1 minus 6. Okay, so let's go ahead and take what's in the brackets and simplify that. Let's see if anything nice comes out of this. We get x squared plus x minus 6. And hopefully you're thinking to yourself, wait, that's factorable. That's nice. I can factor that. So now we have x plus 1 times x plus 3 times x minus 2 equals 0. And now we have this factored into three factors. We can apply the zero product property and know that x could be negative 1, x could be negative 3, or x could be 2. And there are our three zeros, our three roots to this polynomial. And we are now finished solving this. And in reality, guys, I would probably go to my graphing calculator if I was allowed that. If not, well, then it's a whole nother ballgame, and a method like this becomes very applicable. Our second one. Okay, this is big. This is a 4th degree polynomial. I'm scared, guys. I'm really scared. I'm terrified. Well, let's go ahead and use our graphing calculator. I've talked about using it. I haven't showed you how to use it yet, though. So here's our calculator. I'm going to go ahead and add a graph. So I input my polynomial into a graph screen, and I get this beautiful graph here. So let's go ahead and adjust the axis. I really want to see a little bit closer at what's going on here. So let's make this be, or let's make that be 2. And let's make this be negative 5. There we go. Now I can see a little bit better what my roots are going to be. And now we just go in and we analyze the graph. We want the zeros. You might recognize that as being, oh, 2/3. Look at that. Let's find the others. Boom, boom. And then one more. Oh, but there's only 3. I'm expecting 4 roots here, aren't I? Well, what do we get from the graph? Well, we got x equals -1, x equals -3/2, -1.5, and we got x equals 2/3. Now, what we know is that this one, because the graph came and bounced off the x-axis, what that means is that's a repeated root. We see that with the quadratic. When the vertex is on the x-axis, it's the same story here. We're going to have a factor of x plus 1 quantity squared times some polynomial. And even if I didn't know these, we can still find them. We're going to pretend we don't know them for a minute. So this has multiplicity of 2. My graph looks something like that. This was -1. I have these. If I can read all of the zeros that I'm expecting off the graph, great. But sometimes some of the roots are going to be irrational. So let's look at how to deal with that. It's not too bad. We found this integer root that has multiplicity of 2. So what we can do is we can start using synthetic division. 6, 17, 10, -7, -6. We put our -1 out here. So we multiply outside, add inside. Get a remainder of 0. That's good. Now we can do synthetic division yet again because -1 is a root that shows up twice. It actually has 2 roots of -1. So we repeat the process now. And what we now know is that our polynomial is x plus 1 squared times 6x squared plus 5x minus 6. And if this quadratic was not factorable, we can now apply the quadratic formula and find our last 2 remaining roots. But guys, it is factorable. We know that. It factors into 3x and 2x, and then we would have plus 3 and minus 2. And you might ask, how do I know it's factorable? Well, I know it's factorable because when I looked at the graph, the other 2 roots were rational numbers. And if I have rational roots, that means they came from a nice linear factor. So here we go. I can now solve these last 2 to get these remaining roots of x equals 2/3 and x equals -3/2. But again, if you can read all these off the graph like here, produce a nice graph, label the roots, and then answer the question. Now there is one more little nugget I want to show you on your calculator. We can go to a calculator screen, and we're going to go into the Algebra tab, and we're going to go down to Polynomial Tools, and we are going to find roots of the polynomial. We have a 4th degree polynomial, and I want the real roots. And we're going to enter the coefficients here. Once we have our coefficients entered in for the polynomial, we press OK. Now it's saying find the poly roots for x. We push enter, and oh, there we go. Look at that. It will return all of our real number roots. Now, the one thing it won't do for us is if some of these roots are irrational, it won't list those as an exact value. It will give us a long decimal. But what we can notice here is that we could pull off any rational roots or integer value roots and then go back to our synthetic division to find any remaining irrational roots. So there we go. Overview of how to use technology and how to factor by grouping when solving higher order polynomials.